Sai Srinivas Desabathina is a skilled research manufacturing engineer at Liquid Wire, headquartered in Portland. And I happened to meet the Liquid Wire people at Wearables and was so fascinated by what they talked about. I said, we need to have you guys talk about what you're doing to our group here. And thank you, Sai, for being available to do that for us today. Here, he's earned his master's degree in manufacturing and engineering from Oregon State University and has been an instrumental part of Liquid Wire's team for over 3 years. Liquid Wire is renowned for producing the world's first washable, keyword washable, stretchable circuits and sensors, and is paving the way for advances in wearable technology. Sai has contributed significantly to the company's success by designing and developing various testing instruments, such as impact test equipment and linear and biaxial strain systems. His current focus is on investigating and characterizing materials and processes which have been key to generating reliable and robust stretchable circuits and sensors. Sai is also active member of Netflix's Standards and Reliability Technical Working Group. And thank you again for sharing all this very exciting information with us.
Thank you, Roger. I'll start with good morning. I'm on the Pacific Coast, on the West Coast. So yeah, diving into the presentation. Over the past decade, we have witnessed how wearable sensors have radically changed our outlook. They're enabling individuals to continuously and dynamically monitor biological or biopotential signals in real time, with very high sensitivity and with miniature sensing platforms, thus fostering the concept of versatile, remote, and personalized healthcare monitoring. However, the challenge remains is that either it can be your Apple Watch or Dexcom glucose monitoring systems that kind of have a rigid structure. So when they have a rigid structure, there's a kind of a modulus mismatch between the wearable that you're putting on your body and your body. So that kind of does not give you a robust signal, or either the wearable is obtrusive in real time. So to prevent the challenge, or in a Liquid Wire comes to address that challenge, the backbone of Liquid Wire is metal gel. Metal gel is an alloy of liquid gallium indium tin alloy. We modify that alloy with some oxide microstructure and a few proprietary additives. When we have that when we make that mixture, it's in the consistency of a peanut butter at room temperature or a much wider temperature. So you can spread that peanut butter like a conductor on a thin piece of plastic film, and then you can laminate it with other piece of plastic film. Then you have a current carrying conductor or a strain gauge, which can be stretched, which can be flexed, and which can be washed. So this enables us to bring wearables much closer to the body and enable real-time monitoring of human body without any without obstructing your day-to-day activities. In any flexible hybrid electronic, there are two key components that need to be fully functional or that are very important for a system to work. One is a stretchable conductor, and one is how you connect your stretchable conductors to surface mount components or other electronic components. Under various magnitudes of stress and strain, or bend and stretch, those have to survive for it to become a really good wearable electronic. So speaking of the performance of the metal gel, so on the first graph you see we have just laminated a single layer of metal gel in between two pieces of TPU, and we stretched it up to 250% of strain, but the relative resistance just gone up 10x from the initial value. Whereas if you take other commercially available silver inks or carbon paste, they reach the 10x of the initial value just at 20 to 70% of the strain. So it just shows that how reliable is metal gel over huge range of stress conditions. In other words, I can say that the metal gel performance is completely dependent upon the substrate that we use to laminate the metal gel. So if let's say the TPU that we constantly use as a virtually hysteresis-free stretch conditions for 100%, and we can stretch it over 1 million cycles. So depending upon that substrate, we can define the performance of the metal gel. So on the right side, you see a strain gauge. It's a single trace, but in a multi-loop trace that's connected to a PI board on the top, and this structure is made out of TPU. We have stretched the substrate over 1 million cycles. The entire test took 7 days to complete. When we finish the test, you can see the graph. The base resistance has shifted a bit, but still the signal integrity remained really, really good. And when you compare the before and after the test specimen, you can see that the shift in base resistance is because the material did not have enough time to regain its shape because we were stretching it at a really high speeds. But if you do that 1 million cycles at a really slow rates, allowing the material, the substrate to relax, you can see that metal gel can give really a good hysteresis-free response in a strain gauge. So as I said, the next important component for a flexible hybrid electronics is how you connect hard to soft transition, or how you connect the flexible metal gel traces to the surface mount technologies. The metal gel conductor flows into itself and makes ohmic contact with metal it flows against. This feature of the material, we are calling it self-solder, and is the key behind circuit architectures built using metal gel. The internal structure of metal gel provides enough stability that you can directly bond components to the metal gel trace without concerns of losing contact or shorting circuits. This increased mechanical strength of this metal gel also enables patterning of multi-layer circuitry with deformable VR structures directly connecting individual planar layers. And essentially, you can do traditional PCB structures you're building on a thin sheet of plastic film. So this shows an example of how we build our structure. What we call is, on the first figure, what we call is a metal gel core. We print the circuits using a process called stencil in place. Once we have that stencil in place, we take whatever the circuits we designed. It can be an oxygen monitoring sensor, or it can be an IMUs to track your body motion. You can put multitudes of sensors on these cores and have a really good, robust wearable structure built out of it. From literature, we have identified that when you connect a flexible TPU structure to a surface mount or a PCB board, and when you stretch them, they break contact, or there's kind of a scenario where you lose contact because of the modulus mismatch. But we have developed our proprietary process in such a way that you can stretch it 100%, bend it. You can even crease the components, but that would not break the contact. Here we are seeing under the part of NextFlex 5.2, we collaborated with Binghamton University to test a few of our products. What you see is a two-trace test article which has a PI boards on the 3 corners. So we are we are trying to put a bend radius on the PI board that's at the center, and try to see if we can break the contact, or what is the radius that it would take to break the contact. When we kind of did this over 100 cycles, you can see the resistance between the 0.1 and 0.2 did not change, which is an indication that the integrity of the connection at the middle point did not change at all. This speaks to the robustness of the hard to soft transition that a metal gel offers and the process liquid wire offers. To further take the game up a bit notch, we have made much more complex circuits. What we have is an IMU boards, and we have around 10 to 15 traces that are going to and back from the IMU board. I can play a video over it. We stretched it over 15 mm bend radius for 100 cycles, and the product remained really robust and it did not break any contact. So this is one of the tests that we do at Liquidwire to determine how robust are our interconnections. In short, the stretchable conductors that are made using liquid wire can sustain 1 million cycles without undergoing drastic change in resistance or conductor degradation. You can bend them, you can flex them, and it is also interesting to know that we have the conductor that I've showed in one of the slide. We have done 50 wash test cycles. The regular laundry. We dumped we dumped a couple of our strain gauges in laundry for 50 cycles. We dried them, we washed them with laundry detergent, and it was still functional even after 50 wash cycles. The reason that we did wash testing was to we want to put these wearable electronics on clothing apparel so that we can bring the electronics much closer to the human body. And it is expected that these clothes, it is assumed that these clothes should be washed, because when you go to the gym, you want your clothes to be clean after that. So this also tells that we have a really good technology and process in place to build wearables that can withstand wash and dry cycles as well. Yeah, that's a brief presentation of what we're doing at Liquidwire. So,
great, thank you. Thank you, Sai, for your very informative presentation. Before we got one question, but I have a question for you myself. If you look at the concept of functional fabrics, functional fabrics, being an engineer and looking at your technology, I would think that your liquid wire technology could possibly be used in some kind of a woven kind of approach to integrate in with a functional fabric solution. Are you looking at integrating your approach into functional fabrics?
Oh, we definitely are. That's one of the product that's in development phase right now. You can see we have a knee brace that's mounted with liquidwire circuitry on it. So we have a what we call on the outside that you see is called a core. So we build a core which has metal gel traces and the active electronic components on it. So now then we take this active core and then we have the process to bond it to the fabric. It can be a t-shirt, it can be a knee sleeve. So yeah, choose the apparel that you want to wear. We can bond these products to those apparels.
Okay, so it's a bond function, kind of an additive bond function rather than an integrated woven function.
Yeah. So we did not pursue the direction of directly woven into fabrics yet.
Great. So I have several questions here. Let's see, we got 4 questions. Wow. How about this one? The metal gel stays in that state for years without degradation? Question mark.
Yeah, we have some samples dating back to 3 years. When the startup was really in the initial stages. When we even put the samples on Instron and try to collect resistance and strain gauge data, we still see the same kind of performance that we have seen over the 3 years. And not just the conductor, but we still have some samples dating back 3 years with active electronic components such as LEDs and IMUs and Arduino kind of structures. They are still functional. So it can stay in that state for years without any degradation.
So related to that, though, question, how does the conductors do it cold?
So we did multitudes of tests regarding how it can handle temperature. One is we left the sample in the freezer overnight, and then we brought it back and tested it. It was really good. I mean, the problem is only with the substrate that's carrying the conductor rather than the problem with the conductor. So if let's take a silicone, right now we are using TPU, but when silicones are usually known to handle extreme temperatures, either heat or cold. So when you make structures out of silicone, it can work really good. And another test that we have done is since these products have to be shipped somewhere over a ship or an aeroplane, so we started sending samples to friends and neighbors over the through flight just to see how they work. So they really handle those cold conditions in the cargo too.
Thank you. Another question we have, Sai, is the following. Has this been tested for allergies to humans?
What I know is currently the liquid wire is metal gel is ROHS complaint, and we have used it on humans. Like we are doing internal test, to test the product how we are building it. I'm unable to recollect if you have done specific tests to determine if they're allergic to humans. But from my experience working with these products for the over 4 years, I don't think there's any concern of allergies because the conductor is completely trapped inside the plastic films, so it is not exposed to the human body directly.
Great, thank you. Ira, how are we doing on time?
We have time for 1 or 2 more questions.
Thank you. Okay, another question for you, Sai. Stencil or ink question mark.
This is what we call a stencil in place. So we have a base layer and then the trace layer. So we deposit metal gel through trace layer and then try to laminate it with a top encapsulation layer. So this can be called a stencil. We call this stencil in place process.
Well, thank you. Final question. What is the process question mark? What does that mean? What is the process question mark?
I think they were referring to, is it a stencil in place or an inkjet process? So this is a stencil in place process.
Okay, I guess that's it.
I want to also thank Adventest, who's received the highest customer satisfaction surveys, ranking as the #1 large supplier of semiconductor equipment in 2022 from Tech Insights. Also would like to thank Omcor and Cadence. Collectively, their sponsorship has enabled us to produce this event and make it available to everybody free. So I want to thank them once again. And when you have an opportunity, please thank them. And lastly, I would like to thank everyone here for participating. We will have the slides up next week. YouTube videos, the first 2 days are up. The remaining ones will be up by next week. So I want to thank everybody and wish you a good rest of your day and look forward to seeing you at a future MEPTech event. Thank you.